Hi guys, I hope you're good since last video. If you made it to this video and you've watched all the videos before in this playlist, congratulations. That's amazing. You're part of the OGs, and now we are going to tackle this last video, which will be just in the format of an explanation part with some examples. And we're going to talk about the unsafe mode, which was intriguing to me in Rust, coming from Python. And yes, we're going to start straight away. Just before that, like and subscribe, and let's get started. So unsafe in Rust. So what's that? Why do we need unsafe stuff? I know Rust, I like Rust because it's safe actually. So meaning of unsafe. In Rust, unsafe means the Rust compiler cannot guarantee safety for certain operations. So you as a programmer are responsible for upholding those guarantees and ensuring that the code is sound. So this is an advanced way of using it. An unsafe block allows you to do things that would normally violate Rust's strict safety rules. However, the presence of unsafe does not automatically mean that the code is dangerous, only that Rust is not enforcing certain safety checks, and you must take care to ensure that code is used correctly. After Rust have prepared some different ways to permit developers to use this unsafe mode, so it will be in its own scope. There will be the keyword unsafe also to declare that it's unsafe. So Rust still knows what is safe and what is unsafe. Let's go now into this point, common uses of unsafe. So here are the key things you can do in unsafe Rust. So dereferencing row pointers. I think we've seen that once. So row pointers, for example here, star const of type T, and the star mutable of type T are not subject to Rust's borrowing rules. So you need unsafe to dereference them. So here in the example we have an i32. We use 42 as a number. We declare another variable r, which is going to be using this notation with the star const i32. This is the type. And we're using here the reference of this variable as const. So we're doing here casting in order to get this dereferencing done. Unsafe. This is how you're going to mark it. And you see there's those curly braces. And this is the scope. Whatever is inside, that's the unsafe. That's the unsafe. Println. And after we print it, and here you see we dereference R. I mean, we're not dereferencing. Yes, we're using the star. We dereference it. Okay, so here this is a reference of that one has a const i32, and here we're going to be dereferencing that pointer. Dereferencing a row pointer requires unsafe, so you can't do that outside of this unsafe scope. So calling unsafe function or methods. So here we've seen dereferencing row pointers. Here also it's another thing that we can do, calling unsafe functions or methods. So some functions are marked unsafe because they can cause undefined behavior if used incorrectly. These functions must be called within an unsafe block. So let's see what are those functions that we might use. Unsafe. Let's say here this is a function, it's a dangerous function, some dangerous operations. And after we're going to put, so here we mark this function as unsafe first when we declare it. And after we're going to use this function in the scope unsafe. So calling the unsafe function requires an unsafe block. After another case, assessing mutable static variables. So global mutable variables, static mut, can lead to data races. So assessing them is unsafe. Static mut counter I32 is a 0 for the moment, but after that we want to access this static mut, we want to increment it, so we need to do that in an unsafe block using inline assembly. So Rust support embedding assembly language instructions in your code, but this is inherently unsafe. So assembly, it's another language that you can that is closer to the machine. So here Rust permits to interact directly with the machine using some assembly. Here we're using a macro that helps to do that. So unsafe inline assembly requires an unsafe block. Okay, I'm not using assembly at all. I'm at the Rust level at the moment. I'm coming from Python, but yes, assembly exists and you can use it in Rust. That's what makes Rust amazing. Other point, accessing union fields. So unions are a special kind of data type that allows different fields to share the same memory. Okay? Accessing union fields is unsafe because Rust cannot guarantee type safety. So here we have a union, my union, having two different fields. So union F142, unsafe. Accessing union fields requires unsafe. Okay, so here what it says that unions are a special kind of type of data that allows those different fields to share the same memory. Okay, haven't used it, not planning to use it. But yes, this is when you want to learn a bit deeper and know more the code and what you can do with it. So this I didn't know that you can do that. You can have variables sharing the same memory. So this I understand why it can be unsafe and confusing for Rust. At this time I understand why we need to use it in an unsafe block. So what unsafe does not do? I had this question in my mind, so let's see the answer. Using unsafe does not disable all safety checks. This is nice, it's good. Rust still enforces the following outside of the unsafe block. So inside the unsafe block, everything is unsafe, but outside the unsafe block, Rust still enforces his rules. So ownership system, the ownership, borrowing, and lifetime rules still apply outside of the unsafe block. Type system, you can't use unsafe to break Rust's type system. Types must still be correctly defined and used. Memory management, even if in unsafe code, you must manually ensure that memory is properly allocated and freed. Example, when working with raw pointers. So even if you're using the unsafe mode, you need still to follow certain rules. It's not just free to do whatever you want. Okay, so safe and unsafe code interaction. Let's see that. One of Rust's core design principles is that unsafe code should be encapsulated in such a way that the rest of the program remains safe. This means you should aim to write unsafe code in small, well-contained blocks and provide a safe interface around it. For example, if you're writing an abstraction of a raw pointer manipulation, you can ensure that users of the code can call your API safely while the unsafe operations are hidden inside the implementation. Okay? So an example of safe wrapping around unsafe code. So here's an example of how unsafe code can be used safely by encapsulating the danger within a function. Okay, so here we're going to be defining a function, dereference, gets a pointer. The pointer is of type *const i32, returns an i32. Unsafe block is used, but the function is safe to call. Okay, so here unsafe, here we dereference the pointer. Okay, it's unsafe to dereference a pointer, so we want to do that in the unsafe block. And after in the main, we declare an integer 42 row pointer, which is the ampersand of the x variable, the reference of it. We cast it into this pointer i32 into the constant. So, and after here, we're gonna take the value. The value is we're gonna create a value variable which is gonna call the function. The function is gonna take this row pointer, so the pointer which has the right type, *const i32. We have casted it here, and after no need for unsafe here because it's been handled inside the function. And after here we dereferenced the value, and the value we're going to get it by printing it. In this example, the safe dereference function uses an unsafe block internally to dereference a row pointer. So this is not exposed to the user, it's just inside the function. But the function itself is marked as a safe function. Everything is good, it's a safe function. The caller doesn't need to use unsafe when calling safe dereference. So here no need for unsafe here, because the safety checks are handled inside the function. Okay? When to use unsafe? Why would I use unsafe actually? So using unsafe is necessary when we need to interact with low-level code, which is not me. I'm not gonna do that. So calling C functions via FFI, working with hardware. Yeah, that's when we want to be close to the hardware. You need to optimize performance by avoiding certain safety checks, but you must ensure that your code still behaves correctly. So you're writing libraries or sections that involve raw memory manipulation, like custom data structures, but you want to provide a safe interface to users of your code. Okay? So using unsafe is necessary when you want to interact with the hardware. When not to use unsafe. Okay? This is me. I'm not going to use it. Do not use unsafe as a shortcut to get around borrow checker errors or compiler complaints. So do not play the hacker. Okay? Instead, unsafe should be used carefully with a thorough understanding of the potential consequences and why the safety checks need to be bypassed in a particular context. So sometimes you need it. We've seen before the examples. You want to dereference a pointer. You need to use unsafe to get the value, but otherwise just be careful in the way you're using it. Don't use it in the wrong way. Okay, so we've done unsafe. We are done with this subject, and we are done also with the playlist. This is where the playlist is going to stop. Thank you for all the people who followed along from the beginning to the end. And I believe that you have a solid knowledge of Rust now to start using Rust. So this is a beginner playlist. From now on we can start using it. And this has expanded also our way, technique of coding for our Python, that we can also consider improving our Python coding by having those elements in mind on how the code works under the hood. And now we are ready to use Rust as a library in Python. That was the goal of this playlist. So have a break, have a Rust session is done. Thank you for your support, and like and subscribe as usual, and see you next time.